Now this next step is simply to evaluate the stiffness matrix. Step 4, derive an element stiffness matrix equations. So we know the element stiffness matrix K is a function of the B matrix. We take the transpose, the constitutive matrix, the B matrix again. H is the thickness times multiply the operator dx and dy, which has to be integrated over the whole area. So in order to perform the integration now, we know B is now, we clearly saw that B is a function of S and T. This is what we obtained. The B matrix is a function of S and T. If we can clearly see with the values that we have just obtained, since B is a function of S and T, we must now perform the integration with respect to S and T. So here, once again, we need to do a transformation of the variables. That is a transformation from region X, Y to S, T. So this transformation also includes the determinant of that is the determinant of the Jacobian. The general transformation can be written as follows. So if there's a function which is a function of x and y, which has to be integrated with respect to dx and dy over the whole area, let's say, the transformation for a different, let's say, coordinate system, let's say for a natural coordinate system, the function which is expressed in natural coordinate system has to be multiplied by the Jacobian and integrated, so that this is the condition which is used to satisfy the transformation from xy to st domain to a coordinate system. So you can use a theorem from the integral calculus. You can refer it up also in the additional reading material for the proof of this theorem. So in this case, of course, we will directly use this. We will not derive the integral calculus theorem to show the transformation. What you would get as the stiffness matrix in the SN once after we do the transformation, nothing but the B matrix, transformed B matrix, the constitutive matrix, again multiplied by the B matrix, the thickness of the element, the Jacobian, the determinant of the Jacobian, and the integration is done with respect to the new coordinate system from -1 to +1, and again the t varies from -1 to +1. You see, we have to perform this integration in order to obtain the stiffness matrix. Just before we go on to an example, just to get things, all these theories that we learned during the lesson, just before we apply them in a quick example, and before we move on to, let's say, discuss the integration scheme, let's just quickly try to find out how to evaluate the body forces for a given problem, because we already looked at it in the previous cases. The element of body force matrix can be obtained by, so FB is the body force matrix. We need this because eventually the K, the stiffness matrix here, is related to body forces. So we need to evaluate the body forces because F is equal to K times D. So we need to evaluate the body forces. Body forces will be an 8x1 matrix, which is nothing but in the transformation matrix. This is quite familiar, and the X matrix, you know, now it has been transformed. For the transformation, you had to multiply with the Jacobian, ds times dt, and the integration is performed from -1 to 1 for s, -1 to 1 with respect to t. This is an 8x2 matrix. So for the multiplication, this should be 2x1 matrix. So like this stiffness matrix, the body force matrix has to be evaluated by the numerical integration scheme. What about the surface forces? The surface forces matrix, which we, let's say along as a particular edge, let's say along T is equal to one edge, where the overall length is L, we can take it as L. We can evaluate it by simple transformation. The surface force matrix now transforms to corresponding traction forces H L by 2 ds, which has to be multiplied by over the domain -1 to 1, 4 by 1 matrix. So this is again a 4 by 2 matrix, which has to be multiplied by 2 by 1 matrix. So surface forces matrix, we can also express surface forces in the node, because we are considering the edge which is corresponding to nodes 3 and 4, that is t is equal to 1. The edge corresponding to 3 is equal to 1. So along the node 3 in the s direction, the surface tractions along node 3 in the t direction, surface traction forces, the node 4 in the s direction, node 4 in the t direction, nothing but a function which relates to the displacement function, the transformation. This is what I have mentioned here, transformation matrix, and of course the corresponding forces, force matrix P. Let's write it as PS and PT times H L by 2 ds. So since we are evaluating this matrix, of course, because along the edge t is equal to 1, that is at node number 3 and node number 4, we know shape function 1 is equal to 0 and shape function 2 is equal to 0, and no nodal forces are present at nodes number 1 and 2. And for the uniform case of PS and PT, that is along the HT is equal to 1, the total surface matrix becomes, surface force matrix becomes H times L by 2 multiplied by 0, 0, no terms, PS, PT, PS, PT. So, which means that the surface along the edge can be merely obtained by using the corresponding shape functions along the edge. The tractions are applied. So, if we really, if you just draw a quick schematic, this is the element that we considered, S and T coordinate system. So we are interested about the behavior or the surface forces acting on this particular edge. So we know in the T direction, there will be surface traction forces in T direction and surface traction forces as well as in the S direction. This is what you have, what we have written down, PS and PT. Surface traction forces along T is equal to 1H. Okay. So now we have completed the derivation, or we have basically applied the isoparametric formulation for a simple plate element. Let's quickly get an example on, to get familiarized with this method before we talk about the Gaussian integration scheme, which is quite a nice scheme which you have already used in your calculations, in your other mathematical and other work. So let's do an example. Let's call it example 7.1. So for this particular plane element, which I will draw now, try to find the force matrix using energy equivalent nodal forces by using the equations which we just derived. Okay, so the task is for this element, for the element shown below with the uniform surface traction alongside 2, 3, of course, evaluate the force matrix using energy equivalent nodal forces for the edge 2, 3. Okay, so this is the element that you will have to use. The corresponding coordinate systems are 8 by 0. Here the third node is 5, 4 in the XY coordinate system. This is 0, 4. And this is subjected to uniform traction forces along H23, T is equal to 2000 pounds per square inch, acting on the X direction. So this particular element is subjected to uniform surface traction. So you are supposed to find the force matrix using the energy equivalent nodal forces, which we just derived in the previous section, using an integral which is similar to 7.3.29 for evaluating the surface forces. You can use this equation to evaluate the surface forces for this particular problem. Okay, so using equation 7.3.29, we can express the surface traction force along H23 is nothing but multiplication of the shape function, of course the transformation with respect to the surface traction force matrix, the width, the length, the height of the plate element, the length of the corresponding edge with respect to dt, perform the integration within a domain -1 to 1. The length of the surface, the length of the edge 2, 3 is given by the length using the cardinal coordinate system. We can find the length between 2, 3, where L is equal to, so difference between the x coordinates, that is 5 minus 8 squared. Difference between the y coordinates, 4 minus 0 squared, takes the square root, which is equal to 5 by 3, 3 by 9, 4, 0, 16, that is 5. We already know, since we are dealing with node number 2 and node number 3, the shape functions N2 and N3 must be used for evaluating the surface traction forces along the side 2, 3. So, and the edge 2, 3, that is edge 2, 3 corresponds to, in terms of the natural coordinate system, it corresponds to S is equal to 1. So because of this reason, so this equation 10.3.2 becomes, so surface traction forces along the edge S is equal to 1 is given by this equation. And since we are interested in the edge 2, 3, the corresponding shape functions would be N2 and N3, the transformation. And what is the traction forces? We have two traction forces, the PS along S direction and the forces acting on the T direction, the height, length half times dt. So we know the shape functions of the four nodes in the linear plane element are taken from the previous. We already derived this at the very initial part of the derivation, which we can take from equation 7.3.5. If you look it up, you would get N2 is equal to 1 plus S, 1 minus T, divided by 4. If you solve it, it is S minus T is ST plus 1 divided by 4. And similarly, N3, we have already obtained it to be 1 plus S, 1 plus T, divided by 4, S plus T plus ST plus 1, 7.3.35. So the surface traction forces along the edge is given by PS and PT matrix. We know the only applied external force is 2000 pounds per square inch, and there are no forces acting on the T direction based on the problem which has been given to us. Yeah, it's clear. It's only in the S direction where the forces are applied. Right. Now we have the shape function equation for shape function and equation for the forces. By substituting these values, the surface traction forces can be obtained if we assume the thickness of the plate to be 0.1 inches. Then equation 7.3.2 becomes, what I do is simply substitute the values into equation 7.3.32. What you would get is the surface traction force is nothing but equal to shape function multiplied by the traction force matrix, height, length by 2, and perform the integration from -1 to 1. In the next step, let's substitute all the values. Into 0, you need to take the transformation now. Transform shape function matrix times the surface forces, thickness, the length by 2 times dt. So we can simplify the above equation and obtain the traction force. You can do it on your own, the corresponding math, to see whether you get the same results. So by simply substituting the corresponding N2 and N3 values from the equation 7.3.35, because we already have N2 and N3 values there, we can further simplify this relation. What you would get is Fs is equal to 500 integration formed over -1 to 1. Now I'm substituting the N2 and N3 values dt. So by substituting S is equal to 1, because we are evaluating along the edge S is equal to 1, once we do the transformation and we perform the explicit integration, what we obtain is Fs is equal to Fs is equal to, so we substitute S is equal to 1 dt, which is nothing but 500 plus t squared by 4, -1 to +1 to -1. So the next final step is to evaluate this integrals. 0, 0 pounds. So in the explicit form, if you can write, if we write traction corresponding to the surface forces corresponding to second node, surface forces corresponding to third node is equal to 500, 0, 500, 0, once we do the transformation. So this is a typical example of how we can apply the theory that we have learned, or the surface traction forces corresponding to surface traction forces at node at the edge, or at the nodes 2. After we cover the theoretical section, I have already given you some examples to work out, and of course I have given you some solved examples. You can first try to solve these examples by your own, and also look it up at the solved example to see whether you have made any mistake or whether you have got it correct. Since we are almost at the end of the lesson, I think the time will not permit us to discuss about the Gaussian integration scheme. Why we need to discuss such integration scheme is that you realize now, in order to evaluate the stiffness matrix using the isoparametric formulation, these integrations, there are two integrals we need to be solved. So for this, an integration scheme is necessary because there are no direct solutions. So the numerical integration schemes have to be employed. So the most commonly employed integral scheme is the Gaussian integration scheme. In the next lesson, before we start with three-dimensional stress analysis, We can shortly talk about the Gaussian integration scheme and how it can be applied. This is nothing new. When it comes to one-point Gaussian quadrature, it really relates to simple trapezoidal rule, simple midpoint evaluation, if you can remember. Else, when we go through these examples and when we go through this simple integration scheme, you will realize that this is quite intuitive, and you have, or maybe you have applied this simple midpoint integration schemes in your for evaluating an area under a curve. Of course, in the practical class, you will be directly applying maybe how to solve three-dimensional stress problems, and of course, in the next lessons, we will also be looking at how to tackle heat transfer problems. Most likely within this week, you will be getting a heat transfer problem, so that it will also be a nice preparatory work for the upcoming lessons for the theoretical sections.